Hello folks, today we're going to be diving into a new domain, and that domain is recommendation systems. And so today we're going to be implementing the Generalized Matrix Factorization model, or the GMF model as I call it. Now, if you do not know what's matrix factorization, it is a way of doing collaborative filtering. And if you do not know what's collaborative filtering, I would then suggest you take this course by Google. So it's under Advanced Courses. You can see the URL here. So it's developers.google.com/machine-learning/recommendation. And there you can see candidate generation section. And under that section, you see collaborative filtering and matrix factorization. You click on that, and then you click matrix factorization. And so this is a really nice write-up, and they walk you through this approach of matrix factorization in the context of recommendation systems. Okay, so I suggest you read this. But I will still provide a high-level overview of how this works. Okay, so I'm going to use this image they have there. Let's suppose we're building a recommendation system based on the user behavior data that we have from our user base, which is 4 users in this case, and we have 5 movies that. So we're probably doing something with movies. Maybe it's Netflix or something. Of course, in Netflix we have a lot more movies, a lot more series, but for the sake of simplicity, let's suppose we have 4 users and 5 movies. And so based on this user behavior that we saw, how can we build a recommendation system? A matrix factorization based collaborative filtering system. Okay, so the way we're going to do this is that for every user, we need to have embeddings. And same goes for every item or every movie. I'm going to call movies items because that's going to be a more general term, right? So in this case, we're going to have movies, but in a more general case, we can have maybe fruits and veggies if it's a grocery store. Could be cars if it's a car dealership or some kind of a company that sells cars. And so it can be anything really. In this case, these are movies for maybe for simplicity and Shrek and some have some fun. But again, this is much more general. For every user, we're going to have embeddings. Of course, for embeddings, we need to know the embedding dimension. In this case, they've chosen 2, so let's go with 2. Now, the embedding dimension for users and items, they should be these dimensions should be the same, right? So both of them are 2. We have 4 users, and therefore we have 4 by 2 embedding tensor, right? So it's a tensor of order 2. We can also call this an embedding matrix. So it's a collection of numbers in a way, right? So it's 4 by 2 because we have 4 users, and for every user we have 2 numbers. Okay, the embedding dimension is 2. For the movies, we would have 5 by 2. Okay, in this case, they transpose the matrix, the embedding matrix, and we have 2 by 5. The reason they transpose this is so that we can approach this or see this in a kind of an easier kind of a way, because during the training, what we do is that we take the user embedding matrix and we multiply it by the transpose of the items embeddings matrix. And so because the items embeddings matrix is 5 by 2, if we transpose it, we get 2 by 5. And now we can multiply, we can do the dot product. 4 by 2 times 2 by 5, and we get 4 by 5 matrix. This is what we have right here, right? And so collaborative filtering allows us to capture relationships between movies and items, or items, not movies and items, but users and items, but also between different users. So we can make suggestions based on inter-user kind of similarity in a way, right? So all these different relationships are very important, and we need to capture these. And so collaborative filtering allows us to do that. And so during training, we do this multiplication of user embedding matrix by the transpose of the items embedding matrix. Of course, that the dot product is really a sum of products, and that helps really capture the relationships in a way. But this, of course, is then trained during the training process, or in a training loop. we use a loss function. Now, the loss function they use here, I believe, or they suggest, is the square distance, right? But there are other functions as well. Minimizing the objective function instead of we could use or of course we could use other functions as well. MSE loss can be used, but they also suggest other approaches of gradient descent, right? Or other approaches for minimizing objective function, not gradient descent. So they suggest stochastic gradient descent. We're not going to be using stochastic gradient descent. We're going to be using mini-batch gradient descent. But they also suggest weighted alternating least squares. It's specialized to this particular objective, so it can be used as well. They also expose you to different kinds of optimization approaches, right? So, of course, stochastic gradient descent is one, but there are others as well. So, really nice write-up, as I said. Now, again, we're going to be doing it using mini-batch gradient descent. We're not going to be doing stochastic gradient descent. Well, unless we're setting the mini-batch size to 1, but we're not going to be doing it. And so this is pretty much how this works under the hood, right? But one problem that we have with this implementation is that, or this kind of system, as well as implementation once we implement it, is that it's a linear system, right? So the dot product is again, it's a sum of products, and that results in a linear system. And while linear system can capture some relationships, it fails at capturing more complex relationships. And that has to do with, again, it being a linear system. And to alleviate this problem, to kind of fix this problem, we can introduce non-linearity. So we can generalize this model by allowing it to capture more complex relationships. And as the name suggests, generalized matrix factorization model does exactly that. It introduces nonlinearity, and in particular, that's going to be sigmoid. To then, or in our implementation, it's going to be sigmoid. We could actually play with that. And that, of course, allows for capturing more general relationships. Okay, so the way we're going to implement this is that we're going to first implement a regular matrix factorization that is described here, right? So it's UV transposed, but we're going to be implementing it using batch gradient descent, a mini batch gradient descent. So we're not going to be doing batch gradient descent or stochastic gradient descent, and especially the equation they provide here, UV transpose. Of course, that describes the collaborative filtering, but it's not very efficient on GPUs because GPUs, they're very good for performing relatively small, performing computations on relatively small pieces of data very quickly. Relatively, I mean, in comparison with like operating on gigantic user and items tensors. In this case, of course, it's 4x2, and in this case, we could have done batch gradient descent. In this case, it would have been probably efficient, right? But if we have to deal with thousands of users and thousands of items, then this does not scale because in that case, actually using CPUs might be better, okay? Because GPUs are not designed for processing these kinds of computations very quickly. We can still do it, but it's not going to be as efficient. So the goal is divide and conquer. So we're going to be chunking these computations into smaller pieces, and then instead of building this whole or doing this matrix multiplication of embedding matrices in a single pass, doing entire kind of like a UV transpose, instead we're going to be focusing on some mini batch of user item pairs, and we're going to be building this matrix iteratively, and again, mini batch user item pairs at a time, right? So mini batch at a time. Okay, so let's now implement the matrix factorization model and then make a few changes to it, and we're going to get to the we're going to obtain the generalized matrix factorization as a result. Okay. let's go into this directory here, GMF. So we have the training code here. So I wrote this beforehand so that once we're done implementing the model, we can train it. So I'm going to import torch and torch.nnn and class, let's call it MF model. So it inherits from nn.module. So this is going to be the matrix factorization model. Let's define a init method. So it just initializes model parameters. And so I'm just going to build up like the skeleton of this. And once we're done doing that, let's think about what we need. Let's do it this way. Performs a forward pass. Okay. So let's go back to this picture here. We had 4 users, 5 movies, and we needed these embedding matrices. So for these embedding matrices, those are like the core of the collaborative filtering. These are needed, right? And as the name suggests, it's called matrix factorization because we factorize that larger matrix into 2 factors, right? So we need these, right? So and we use these 2 factors or these 2 embedding tensors or matrices to then build up the larger matrix and operate on that. Okay, so these embedding matrices, they depend on the number of users and embedding, well, this one depends on number of users and the embedding dimension. This one, it's transposed, but it depends on the number of movies or the number of items in a general case and the embedding dimension as well. So we definitely need the number of users and the embedding dimension. We also need the number of items for the items. Okay, now let's go ahead and define the embedding for users. So user embeddings, and then that embedding. We need, so it takes num embeddings. So Torch has this nn.embedding. It's really a lookup table so that we can retrieve these embeddings for particular users and items and operate on those. And those are going to be num users. And the embedding dim is going to be the embedding dim. Now we need the same for, we need to do the same for the items. Okay. And the next step is, it's not strictly necessary, but what I'm going to do is that I'm going to uniformly initialize the embeddings for equal contributions of intent. So what that means is that in a beginning, we're going to be more or less uniform in making like decisions in a way, right? So we're going to be like, okay, we're not going to be biased as much when it comes to particular items or particular users, so, because again, we do not only care. So we not only care about the user item similarity or relationships between users and items, but we also care about inter-user relationships. And so weight data uniform 0.5 to maybe 1. I think that's an okay range. And that's going to be it for the initializer. Now, in the forward method, we'll need the user embeddings. And that's going to be self.userEmbeddings with users. And of course, the forward method will need to get users, which is going to be torch.tensor, and the items. Right? So we need user item pairs in a way, right? So we need user embeddings. We can obtain those by applying and an embedding basically on it on those users and items. Then we define maybe out, and we can do user embeddings times item embeddings, and we can sum it across the first dimension. Oops. Okay, so we multiplied these and summed it across the first dimension. All right, so the first thing that you're going to say is probably like, okay, like, what is this multiplication and summing across the first dimension all about? Certainly, what they have here is a bit different. It's UV transpose. So we have to multiply the user embedding matrix by the items embedding matrix transposed. So what is this all about? Well, as I said, so it has to do with doing mini-batch gradient descent. If we did UV transposed, Of course, that would not be very efficient for thousands of users and thousands of items, because again, GPUs are very efficient when we have relatively small, when we operate on relatively small pieces of data, when we perform computations on smaller pieces of data. And so what we do again is that we're not doing this entire matrix building process in a single pass, in a single go. Instead, we're doing mini batch gradient descent, and we do it one mini batch user item pairs at a time. Okay, but other than that, it's going to be kind of the same, right? So how does matrix multiplication or the dot product work? Well, it's a sum of products, and that basically helps us do it, right? So even here, I mean, you can see how this works, right? So it's 0.9 times 1 plus minus 0.2 times 0.1, so it's 0.9 minus 0.02 and we get 0.88. So we kind of operate on, in this case, that would be like stochastic in a way if we just do it one kind of cell at a time or one box at a time here. But no, we're doing some mini batch number of user item pairs at a time. Okay, and this basically achieves, it has that effect pretty much. We're building it mini batch at a time. But again, this is a matrix factorization model, right? So we want to capture more complex relationships. And so how can we do that? How can we transform this model, or what changes do we need to make to turn this model into the generalized matrix factorization model? Well, the first change is going to be putting G in front of the MF model, so that stands for the generalized matrix factorization model. The next step is defining an affine transformation. I'm going to call it affine transform. It's going to be a linear transformation. So in features is going to be number of, so it's going to be the embedding dimension, and the out features is going to be 1. And we'll also need the sigmoid to map the values or to squash the values into a 0-1 interval. Okay. And instead of doing this, I'm not going to sum it. Instead, I'm going to apply an affine transformation to out. Maybe I can do it here. So let me do it again so that it's more kind of visible what I'm doing, or easier to see what I'm doing. Self.affine transform. We don't do sum though. We don't do sum. We do an affine transformation, and then out self.sigmoid of out, and then we return it. That's the entire implementation of the generalized matrix factorization model. So again, what this does is we map these features to 1, and then we apply sigmoid to it. Okay. But one thing I'm going to say is that we're not going to be using sigmoid here. It's not because it's not necessary. It's necessary. It's because we're using a specific loss function. It's BCEWithLogitsLoss. Now, if you do not know what this does, you can read the PyTorch documentation. So this loss combines a sigmoid layer and the BCE loss in a single class, in one single class. This version is more numerically stable than using a plain sigmoid followed by a BCE loss, as by combining the operations into one layer, we take advantage of the log sum expric for numerical stability. And so I usually use this loss function. This means that we do not really need this. So the only change that we made was in this function, is that, well, we don't need this, is that we, instead of doing sumdim1, we did self.affine transform, and we defined affine transform there. So really, we modified one line and added one line. That's all we needed to do. Now let's go ahead and train this. But before we train this, I want to show you what data set I have. I think this wget should be that wget. I need, so that wget should be the same. Yes. Okay. So, and by the way, if you're wondering why my wget does not have all the other info, I have a config, but sometimes I actually enable spitting out more information, so that, some cases it's necessary. In this case, it's kind of nice to have wget configured that way, but anyway, it's not really relevant. It's relevant for getting the data though. So let's extract this here. Once we extract it, I don't really need it. And ratings.csv is the file that we're interested in. So let me show you what this does. So we can import it. We can use pandas for that. And what I do is I drop the timestamp. In production, of course, the more user behavior we can capture, the better. The timestamp can be very useful for determining when user logs in and what times, what is what are the times throughout the day they're active and things like that. Of course, it's very important, and it's important to capture as much user behavior as possible. In this case, these would be more of like side features, and with matrix factorization based models, it's kind of difficult to capture these. For those, I think different kinds of models are more suitable, and I'm going to be covering those in the next video, or I'm going to be covering one of those in the next video. But yeah, the next thing I do after dropping the timestamp is I normalize ratings. And you can see that. I use min-max for that. So min-max scaling or min-max normalization, you take the whatever feature you have, you subtract the minimum of whatever tensor it is inside, divide by the maximum value inside that tensor minus the minimum value inside that tensor. Of course, that's going to be between 0 and 1 because of how this is represented. And you can see that df rating, if you do max, that's 1, and if you do min, that's 0. Okay. Other than that, I also kind of re-encoded the movies as well as the users. You can see that movies, they are like 1, 3, 6, so it's kind of like irregular. So after re-encoding those or encoding those according to this very simple kind of schema, we have, it starts with 0. It's kind of more readable or more, we don't have gaps between user IDs and movie IDs pretty much. I don't know if we had gaps between user IDs, but in between these movie IDs there were some gaps. So that was the some operations that I did on this data frame, and then I defined PyTorch data set, and then we trained the model. Okay, so let's train it now that we have the data. Let's see. So it goes from 0 to 1. Movie ID goes from 0 to 9723. So we have 9,724 movies and 610 users. And you can see train. So yeah, we implemented the matrix factorization model. We made a few changes to it, and we got the generalized matrix factorization model as a result. And yeah, so thanks a lot for tuning in. If you have any questions or suggestions, please feel free to comment in the comment section, and I'm going to see you next time.